In this video, we shall discuss the normal distribution. It is also known as the Gaussian distribution. It is a very important continuous probability distribution because it arises frequently in theory and practice. The normal distribution is a type of continuous probability distribution for a real-valued random variable. Let's refer to the definition. A random variable x with mean mu and standard deviation sigma is called a normal random variable or a n bracket mu sigma square distributed random variable if its density is given by this expression. The probability density function is a bell-shaped function and is symmetric about the mean mu. X can take any values between negative infinity to infinity. We write this notation to represent that X is distributed normally with the mean mu and the variance sigma square. We read that X follows normal distribution with mean mu and variance sigma squared. Please note that the formula for the probability density function of the normal distribution has to be precisely the same as here. If the distribution of a random variable has a similar shape as this one, but if its probability density function doesn't fit this formula, then it is not regarded as a normal distribution. For example, the first diagram here illustrates a random variable x1 which follows the normal distribution with mean mu equals to 3 and the variance sigma square equals to 9. The total area under the curve would be 1. The second diagram illustrates the random variable x2 which follows normal distribution with mean mu equals to 6 and the same variance sigma square equals to 9. Compared with the first diagram, it is shift 3 units to the right. It has the same shape. The third diagram here illustrates the random variable x3 which follows the normal distribution with mean mu equals to 3 and the variance equals to 36, which is 6 squared. It is centered at the same location as the first diagram, but it has a lower peak and more area at both tails of this probability density function than the first and the second diagram with variance equals to 9. But the total area under the curve is still equals to 1. This diagram illustrates the standard normal distribution, which has the mean mu equals to 0 and variance equals to 1. We prefer to use Z instead of X to represent the random variable with standard normal distribution. This is the corresponding expression for the probability density function for the standard normal distribution. For normal distribution, X can take any value between negative infinity to infinity. The function here is the probability density function. That is to say that if we integrate this function from negative infinity to infinity, we get 1. However, please notice that it is difficult to obtain the integral of this function. The reason is that there is a square here at the exponent instead of just t here, and there is no t here for us to make a good substitution of the variable. Please be convinced that we shall get 1 for this integral. Theoretically, to obtain the probability that the value of x is between a and b, we can get the value from integrating this function under the interval a to b to obtain it. However, there is no closed form solution for this integral, and one needs to find the value numerically. what we do is that we rely on the use of software or to refer to standard normal table which contains records of corresponding values. Besides, we have the 68, 95, 99.7 rule, which states that the probability that the value of x is within one standard deviation away from the mean is 68%. The probability that the value of x is within two standard deviation away from the mean is 95%, and the probability that the value of x is within 3 standard deviation away from the mean is 99.7%. If the event concerned has an interval which relates with these locations, then we can obtain the probability accordingly with the use of these percentages, such as the examples illustrate here. Let's refer to the example. Let x be a random variable which is normally distributed with mean equals to 2 and variance equals to 3. We would like to find the expected value of e to the power 2x. Let us consider the expected value of e to the power 2x. It can be obtained by using this formula where we put e to the power 2 times t here and integrate e to the power 2t times the probability density function with respect to t over the whole interval from negative infinity to infinity. Since x is a normally distributed random variable with mean 2 and variance 3, according to this formula, this is square root 3, this is 3, and this is 2. So we have the following formula, and e to the power 2t is in this exponent. Please notice that with this type of expression as the integrand, this type of integral is difficult to obtain directly. The reason is that there is a square here for our variable t here, but there is no t here for us to perform substitution of the variable t. When we come across this type of integral, it would be easier for us to evaluate its value by relating this integral with other familiar integrals with known values. For example, we should be aware that this expression is equal to 1 because this expression represents the probability density function of another random variable with mean equals to 8 and the variance equals to 3. Therefore, to integrate this expression with respect to t, for t from negative infinity to positive infinity equals to 1, and we do not need to evaluate it directly. So this gives the result e to the power 10. Now let's refer to the following theorems. If x follows normal distribution with the expected value that is mean equals to mu and the variance sigma squared, then we can construct a new random variable which is defined as x minus mu over sigma. Then this random variable will follow the standard normal distribution, that is a normal distribution with the expected value equals to 0 and variance equals to 1.